This year, the Casting Steel Competition, organized by the Steel Founders Society of America, challenged engineering and metallurgy students to apply their technical knowledge to a unique task, designing and casting a functional replica of one of George Washington's swords. Washington owned several swords in many varieties, including cateaus, epées, and broadswords. For this competition, we have chosen his Bailey silver and ivory-hilted cateau.
Our process began with creating a 3D rendering of the sword based on historical references using the SOLIDWORKS CAD software. Once the model of the blade was completed, we began work on the casting mold. We wanted to have multiple blades cast at once, so we created a model that had 6 swords mounted radially to a central sprue. Thankfully, our sponsor Magneto helped us using their Magma computational fluid dynamics software. We're able to run several simulations of our casting molds until we landed on our final design, which when compared to our initial models, displayed reductions in turbulence, porosity, and the probability of casting failures before any metal was actually poured. At the same time, we began work on our material selection process to determine what alloy to use for the blade.
The selection process maximizes hardness, yield strength, and toughness, which will give our blade a sharp edge, allow it to bend before breaking, and reduce the potential of cracking. This is incredibly important because cast parts contain voids that act as crack initiation sites. The material we selected for our sword is 17-4 stainless steel, which has the added advantage of tunable hardness. With a fully optimized mold design, we partnered with Matthews Additive Technologies to print the mold. We selected the binder jet printing technique because it offers the ability to print complex designs at low cost. It's also simpler than investment casting.
Casting was done at Andritz Metals. The mold was preheated and the steel was poured at 3,000 degrees Fahrenheit. The key feature of 17-4 stainless steel is its precipitation hardenability. To even out the chemistry of the as-cast tree, we perform solutionization at 1900 degrees Fahrenheit for half an hour. With evenly distributed composition, we then age harden the steel at 900 degrees Fahrenheit for 1 hour. During this step, coherent precipitates rich in copper form in the martensite matrix. These serve as inhibitors of dislocation motion, which increases strength and hardness.
To remove our blades from the casting tree, we used a plasma cutter. Then we were off to the lab to machine the blade. We thinned it out and added an edge using a large bell sander.